Well, you can see here we're talking about double angle and half angle formulas for trigonometry. Specifically, I've broken this into two parts. This part's about double angle formulas, and the second part will be about half angle formulas. So the first question, the first issue is what is meant by a double angle? And it's referring to when we have something like the sine of 2 times an angle, sine of 2 theta, or the cosine of 2 times an angle, or the tangent of 2 times an angle. And so there's a formula, much like there's a formula for the sum of two angles, or the sine of the sum of two angles, or the sine of the difference of two angles. Well, there's a formula for the sine of 2 times an angle, and cosine and tangent as well. So we'll begin investigating these, and then do some problems where we use these formulas. Well, as with the formulas for the sum and difference formulas, I cannot emphasize enough that it's important that you get these memorized as quickly as possible. And these are probably more important than the sum and difference formulas. And here you can see the double angle formula for sine is that the sine of 2 times an angle theta is equal to 2 times the sine of that angle theta times the cosine of that angle theta. And what follows, what we're going to do is see where that comes from so that we can make sense out of it, but we'll memorize what's in blue there. So when we see the sine of 2 theta, since 2 theta can be thought of as theta plus theta, then we can look at this as the sine of the sum of two angles where the two angles are the same. And so we use the sum formula for the sine function, which is sine of the first times cosine of the second plus cosine of the first times sine of the second. And when we apply that, the sine of the first angle, of course, first angle is theta, times the cosine of the second angle, but the second angle is theta also, plus cosine of the first angle, but the first angle is theta, times the sine of the second angle, but the second angle is theta. So we end up with the line that we see here. And then we notice that cosine theta times sine theta could be written as sine theta times cosine theta, which matches exactly what we have in the first position. And so when we notice that those are exactly the same, are identical, we can combine them by saying that we have 2 times the sine of theta times the cosine of theta. So it's a very easy derivation, but one that's very important. Now the next one we're interested in is the double angle formula for cosine. And what I'm going to point out here, and I don't want, well, here, I'm pointing it out here. There's actually 3 different versions of it. And we use the version that is most appropriate for us or most useful for us at the time. We'll see why there's 3 different versions here in a moment. But the cosine of 2 theta could be written as cosine squared theta minus sine squared theta, or it could be written as 2 times cosine squared theta minus 1, or it could be written as 1 minus 2 sine squared theta. Each of those are equal to the sine of 2 theta, a cosine, pardon me, of 2 theta. So let's see where that came from, and you might anticipate that we're going to use exactly the same approach we used above. We can think of 2 theta as theta plus theta. So we have the cosine of theta plus theta, which would be the cosine of a sum of angles, where the angles are the same. And so we would use the sum formula for cosine, which says a cosine of a sum of angles is cosine of the first times cosine of the second minus sine of the first times sine of the second. Well, here, since the angles are the same, this ends up being cosine of theta times cosine of theta minus sine theta sine theta. And of course, that could be written, cosine theta times cosine theta is nothing more than cosine squared theta. Likewise, sine theta times sine theta is sine squared theta. So you see we have the very first expression up here by the method that we just used. Now, here's something else that we could do. Let's take this cosine squared theta minus sine squared theta. I've rewritten it here, and I'm focusing on sine squared theta. Well, sine squared theta from previous work we know is the same as 1 minus cosine squared theta. So I put 1 minus cosine squared theta in the place of sine squared theta. And then algebraically, when I distribute that minus sign, it becomes minus 1 and plus cosine squared theta. And so, of course, you see we have cosine squared theta plus cosine squared theta, which is 2 cosine squared thetas, and then, of course, subtract 1. And we would do a similar, and of course, that's the second one. We would do a similar thing to get 1 minus sine squared theta. What we would do, instead of replacing sine squared theta here, we would replace cosine squared theta with 1 minus sine squared theta, and it would result in us getting 1 minus 2 sine squared theta. Now there's also a double angle formula for the tangent. Oops, there's one. I said formulas, but there's one, isn't there? And here it is. And we basically have done the same thing. And notice tangent of 2 theta is a fraction 2 tangent of theta. Whoops, I see I've got an extra parenthesis there. Please forgive me. Divided by 1 minus tangent squared theta. And that relies on the fact that the tangent of a sum is the tangent of the first plus the tangent of the second divided by 1 minus the tangent of the first times the tangent of the second. And since these two angles are the same, we have tangent theta plus tangent theta in the numerator and 1 minus tangent theta times tangent theta in the denominator, which of course becomes 2 tangent theta, that same trailing parenthesis that I shouldn't have there, divided by 1 minus tangent squared theta. And so that's where that particular identity comes from. So as I said, it's very important for us to get those memorized and in our head. And certainly you need to write those down. Maybe you need to go back and write them down and get them into your notes and use that information or get it memorized so that you can rely on it very quickly in the future. Well, we're going to use the double angle formulas to do some calculations, much like we have in the past in other sections. We're given this information. We're given that the cosine of theta is negative 2/5, and the fact that theta is between pi and 3 pi over 2. Well, between pi and 3 pi over 2, of course, cosine is negative, as we see here, but sine is also negative. Okay, that's an important idea. So what we were asked to do here is to find, the first part, to find the cosine of 2 theta based on this information. Well, let me point out to you, look over here to the right, don't look at the left right now. Here's a summary of each of those double angle formulas, and let's look specifically at cosine of 2 theta. We have 3 choices. And if we look at the very first choice, to calculate the cosine of 2 theta, we need to know the cosine of theta and the sine of theta, but all we're given is the cosine of theta. If we look at the last choice, we need the sine of theta to calculate, and we're not given the sine of theta, so it would take some work. In the middle choice, here's the idea. We have 2 times cosine squared theta minus 1 to calculate with. And all we need there is to know the value of cosine of theta. So this is the one we choose to use. And so here's, it's that middle identity that I'm using. And since I know that the cosine of theta is negative 2/5, in the place of the cosine of theta, I put a negative 2/5, and of course it's squared. And so after this, it's just a matter of some algebra. When we square negative 2/5, we get positive 4 over 25. And when we multiply that by the 2, we get 8 over 25. And then, of course, we need to subtract 1, so we write 1 as 25 over 25. And so 8 minus 25 is a negative, you can barely see that blue negative sign, is a negative 17 divided by the common denominator of 25. So that was pretty easy. It was a matter of us making a good choice for which identity. Now, unfortunately, I guess it's on the next page. I'm searching. When we do the B part, we don't have, if we look at the B part and we want to know the sine of 2 theta, well, since that's 2 sine theta cosine theta, we're given the value of cosine theta. We don't know sine theta, So we have some work to do to figure that out. We'll see that here next. Whoops. Let me not spill the beans too much. I can barely see it. I don't know if it's coming out clear on your screen or not, but we're to calculate the sine of 2 theta. Those almost look like zeros, but there is a little mark through there. Those are thetas. And we use the identity then that the sine of 2 theta is 2 sine theta cosine theta. And we already know that the cosine of theta is negative 2/5. So we can put that in this position. And I've done that. Okay. But we're still faced with needing to know the sine of theta. Now, here's what we do know, is that since we know cosine of theta and we have an identity that has both sine and cosine in it, then from that identity we ought to be able to calculate the sine of theta. So if you will, concentrate on the middle part of this rather than, rather than on the left side where I've made some calculations already. Let's go through and see in the middle part. Well, what I've done is I've replaced cosine of theta with negative 2/5 and then done that squaring. So I got positive 4 over 25 there. So I've got sine squared theta plus 4 over 25 is 1. And so, of course, the next thing I'm doing here is I'm subtracting 4 over 25 from both sides. So I have sine squared theta is equal to 1 minus 4 over 25. This looks familiar. I mean, we've done this kind of thing before, haven't we? Now, I just do this subtraction. I write 1 as 25 over 25, and I do the subtraction. I get 21 over 25. So that's what sine squared is equal to. So sine of theta is either plus or it's minus of the square root of 21 over 25. Now, I'm not solving an equation directly. I'm wanting to know the value of the sine of theta. And, you know, theta happens to be a fixed angle that we don't know. So it's either going to be, sine of theta is either going to be plus or it's going to be minus. It's not going to be both. So we're looking, here's the next piece of information. We can decide that the sine of theta is actually negative. Of course, square root of 21 is written here, and square root of 25 is 5. We can decide it's negative for this reason. Look, theta is between pi and 3 pi over 2, which is in the third quadrant. And in the third quadrant, both sine and cosine are negative. And so we have to conclude that the sine of theta is negative square root of 21 over 25. So I come back up here to where I was working. I'd already replaced cosine of theta, and now I have a replacement for sine of theta, knowing it's negative square root of 21 over 5. And so it's just a matter of multiplying all these together. And of course, negative times negative is positive times another positive. And so I have a 2 times a 2, that's where this 4 comes from, and a square root of 21 in the numerator. And denominators are just 5 times 5, or understood 1 times 5 times 5. So this is the result that we get. Like I said, we see this idea repeated over and over and over, and I hope that you're picking up on that because we use this idea quite frequently. That is what we've got in the middle. Oops, looks like I got a little red spot there. I think we'll see why that's there in a moment. Well, here again, we're using double angle formulas, and the problem is stated in this fashion: develop a formula for the sine of 3 theta in terms of just sine of theta and cosine of theta. In other words, we don't want the sine of any double angles or triple angles, just the sine of theta and the cosine of theta. Now they may be squared and so on, sine squared theta, but an argument that is only theta. Well, we can start this kind of like we did with the issue with the sine of 2 theta. See, we could write 3 theta as 2 theta plus theta. And then we can use the sum formula, and we can deal with sines and cosines of 2 theta now. So we can just kind of expand this, iterate it with information that we've gained already in this talk. And since we know that the sine of a sum of angles is the sine of the first times the cosine of the second, and then plus the cosine of the first times the sine of the second, which I've written down here, then we're dealing now with the sine of 2 theta times cosine theta plus cosine of 2 theta times sine of theta. And so we could use, if you will, I should have written this out here ahead of time. That's the sum formula for sine. And what I'm doing next is I'm taking the sine of 2 theta that we have here, and I highlight it. That's why that red was there. I've highlighted the result of using the double angle formula on sine of 2 theta. Remember, the sine of 2 theta is 2 sine theta cosine theta, so I've made that replacement here without changing anything else. Okay, and that's all I've shown there. Now, of course, now I have 2 sine theta cosine theta, so I've written the cosine theta times cosine theta as cosine squared theta. Now I'm going to turn my attention to this cosine of 2 theta that's right here, because we're supposed to have arguments of only theta. So I look at the cosine of 2 theta, and remember, I have 3 different ways to change that. I happen to use, and this was just, it didn't say in a specific form, it just says all of our arguments need to be theta only, not 2 theta or 3 theta. And so I just chose the identity for cosine 2 theta to be 2 cosine squared theta minus 1. I could have chosen either of the other two. But that's all I've done here, is I've replaced cosine of 2 theta with 2 cosine squared theta minus 1. And next, what I've done is actually do the multiplication between these parentheses and the sine theta here. So sine theta times 2 cosine squared theta ends up being 2 sine theta cosine squared theta. And then minus sine theta times 1 ends up being minus sine theta. So that's all I'm showing here, is I did this multiplication. Well, now what I'm looking at here is that I only have arguments that are theta, and so I'm comfortable that I've accomplished primarily what was asked for. The only question is, can I simplify this further? And when I notice that the term I have here, sine theta cosine squared theta, and again here, sine theta cosine squared theta, I have 2 in the first position, 2 in the second position. So when I add those, I have 4 sine theta cosine squared theta, and then minus the sine theta at the end. And there's nothing more I can do there. I suppose I could factor out a sine theta, but that really isn't so significant here. In general, factoring is not necessarily making it simpler. So I've accomplished what I wanted to do at this point, and that is rewrite sine 3 theta in terms of sine theta and cosine theta only. Now this next slide, if you will, is something that's useful in this course. Maybe we don't use it a great deal, but in your calculus courses, and particularly in calculus 2, it is used a significant amount, and it's called power reduction formulas. So as you can read here, it's an interesting result of the double angle formulas for cosine of 2 theta. And that result is something that we call power reduction formulas. So we can take the sine squared of theta, or of alpha, or whatever the angle is, and write it in terms of trig functions to the first power instead of the second power. So that's what this is about. So let's just recall, in our one of our double angle formulas for cosine of 2 theta is 1 minus 2 sine squared theta. And what I'm going to do here is I'm going to take this identity and I'm going to solve it for sine squared theta. So that means I need to subtract. Actually, here's what I'm doing, just to not have to worry about dealing with negatives so much. I'm going to add 2 sine squared theta to both sides. Of course, when I add it to the left side, I have cosine 2 theta plus 2 sine squared theta. And when I add it to the right side, that goes out, and I have only a 1 left. Now, the next thing I'm going to do from line 2 is I'm going to subtract cosine 2 theta on both sides, leaving 2 sine squared theta alone on the left side. So I have 2 sine squared theta is equal to 1, and subtract the cosine 2 theta that I had. And now I'm going to divide out the 2 that I have in front of this sine squared theta. So I'm going to divide by 2 on both sides. And so the result you see is sine squared theta is equal to the fraction 1 minus cosine 2 theta over 2. So it may not be clear why we would want to do this, but we've kind of traded in a power 2 of sine of theta to a power 1 of cosine theta. The only issue is we have the cosine of a double angle. But it's called a power reduction formula because we're transferring, or we're replacing a squared sine function with a cosine function to the first power. Now, for the power reduction formula for cosine, that is rewriting cosine squared theta in terms of a first power trig function, we do something similar, except instead of using the identity for cosine 2 theta that we used above, we use the identity for cosine 2 theta that is 2 cosine squared theta minus 1. Now, in this case, I'm going to add 1 to both sides, and so it ends up looking like 1 plus cosine 2 theta equal to cosine squared theta. And then all I've done on the next step is I've just turned the equation around, so I have the cosine squared theta on the left side. And then after I do that, I'm dividing both sides by 2, and so I end up with cosine squared theta is equal to 1 plus 2 cosine 2 theta over 2. See, these look very familiar. The one up here only has a minus sign in the numerator. The one down here has a plus sign in the numerator. Other than that, they're identical. But we've replaced a squared cosine with a cosine to the first power. So in a nutshell, I've just written those down. Oh, that's not very good at all, is it? I'm sorry here. I couldn't read that. So let me make that so that's not any good either, is it? I apologize to you here. Well, I've just made a mess of it. It's not clear at all. What I'm needing you to do is to memorize these 2 formulas that I've illustrated here. So memorize this formula, of course, and this formula, of course. Okay. Okay, here we're going to solve an equation again. So you see that we're repeating some of these things that we've done in the past, but we have more tools now. So for instance, we can solve more complicated equations than we were able to solve before because of these new tools. Okay, so the equation we're to solve is cosine 2 theta times cosine theta minus sine 2 theta times sine of theta is equal to 1/2. Now I will give you a hint that we usually don't like to have 2 different arguments within one equation when we're trying to solve. So it's problematic that we have 2 thetas and thetas both in one equation. So it might be worthwhile in some ways dealing with this by trying to eliminate the 2 theta or doing something. Now, our first thought might be to use a double angle identity for cosine of 2 theta formula and use a double angle formula for the sine of 2 theta. But you can imagine that this might get much more complicated. Now, it doesn't mean we can't solve it that way, but what I want you to notice is the form of this left side. Cosine, cosine minus sine, sine. The angles here are the same and the angles here are the same. So this looks like cosine first angle, cosine second angle, minus sine first angle, sine second angle. And where do we have cosine, cosine minus sine, sine? It's the cosine of a sum, isn't it? Cosine of alpha plus beta is cosine alpha, cosine beta, minus sine alpha, sine beta. So if we compare what we have here to the form of the formula for cosine of the sum, then we can see the relationships. And so we could rewrite this left side as the cosine of 2 theta plus theta. And that will simplify the left side significantly, won't it? And so that's what I'm doing here. I'm going to replace this left side by looking at the diagram I've drawn here and rewrite the left side, of course, as the cosine of 2 theta plus theta, and of course that's equal to 1/2. And 2 theta plus theta, of course, is 3 theta. So now my equation looks a little more reasonable. That looks awful. This looks reasonable. And so now I can just go about my business and say, okay, well, when is the cosine of an angle equal to positive 1/2? So I draw myself a little unit circle diagram. Here's where the first coordinate's 1/2, and so we're dealing with an angle that crosses the unit circle here and where it crosses the unit circle here. And of course, this is the angle pi over 3, and this is the angle 5 pi over 3. Now, we've been through this multiple times. I hope that you can do that on your own without a great deal of difficulty. This is one of the skills necessary for trigonometry. So that tells us the cosine of an angle, if it's going to be pi over 3, that means the angle has to be either pi over 3 or 5 pi over 3, or I didn't actually say, I guess this is implying, I'm looking up here, and it's implying that we're to find all the solutions, not just the solutions between 0 and 2 pi. So that means we're going to create formulas, doesn't it? So this angle that we're taking the cosine of can either be pi over 3 or pi over 3 plus any integer multiple of 2 pi. So we say 3 theta, the angle we're taking the cosine of, is pi over 3 plus 2k pi. Or it could leave us at this position, which is 5 pi over 3. So the angle 3 theta, it could be equal to 5 pi over 3 plus any integer multiple of 2 pi. And we write that as plus 2k pi. Now, as we investigate further this left side, I'm really trying to solve for theta. So what I'm doing is I'm multiplying through this equation by 1/3. And of course, 1/3 times 3 theta is my theta. That's the reason I did it. But 1/3 times this right side, 1/3 times pi over 3, you see is pi over 9. And 1/3 times this 2k pi is 2k pi over 3. So we get a formula that's related to us ending up in this position. So there's an infinite number of angles that solve it based on this. And likewise, there's an infinite number of angles that solve the original equation based on an angle that has a terminal side of where 5 pi over 3 is. And I've just gone through that here. Did the same thing, multiplied both sides by 1/3. Of course, I have a theta on the left and 1/3 times the right side. And when I multiply that 1/3 out, of course, I get 5 pi over 9 plus 2k pi over 3. And so here we have formulas that give us all of the solutions to the original equation. Okay, in our next problem, again, we're solving an equation, and this time we're to solve the equation cosine 2 theta plus cosine 4 theta is equal to 0. But we're only wanting to solve on the interval from 0 to 2 pi, including in 0 potentially, but not including 2 pi. Well, here's my thought, and you know, there's so many different things we can do. We might first be perplexed by the cosine of 4 theta, and secondly, we may decide that we need to get rid of the cosine 2 theta by replacing it with a double angle formula. But right now, what I would propose is that we just try to get one particular argument. So it would be all right to have trig functions of 2 theta only. It'd be all right to have trig functions of theta only. But we'd first have to going to reduce the fact that this argument is 4 theta, so let's deal with it. And here's what I've noted, that we can think of 4 theta as 2 times 2 theta, or we could think of it as 2 theta plus 2 theta. But if we think of it this way, then we have a double angle in this case. We have the angle 2 theta being doubled, multiplied by 2. And so we could use any one of the double angle formulas for the cosine function. Now, when I look up here and decide which one I want to use, 2 of them involve sine. And then I would have cosine and sine, and that causes an issue. 1 of them involves only cosine. And if I used it, I'd have cosines and cosines, and that's a little bit better for me. And so that's the reason I'm choosing to use the identity involving cosine squared. So the cosine of 2 times an angle is 2 times cosine squared of the angle, and that angle's 2 theta in this case, minus 1, because it's 2 theta that we're doubling. Now, I've got several lines here, let's go one by one. So we're replacing on this left side cosine 4 theta with 2 cosine squared 2 theta minus 1. And now when we look at this left side, we have cosines of 2 thetas everywhere, and that's all right to leave that. We really don't need to reduce any more. We can just solve for 2 theta, and then we can figure out what theta is. So what I've done is I've taken this left side and rearranged it by putting the squared term in front. So now it reads 2 cosine squared 2 theta plus our 2 cosine theta, and then finally minus 1 equals 0. And this looks like a quadratic trinomial that we might be able to factor. And in fact, we can. It factors as 2 cosine 2 theta minus 1 times 2 cosine 2 theta plus 1. Just notice, if I multiply first terms, I get 2 cosine squared 2 theta. If I multiply last terms, I get negative 1. If I multiply the terms here, I get 2 cosine 2 theta times 1, just 2 cosine 2 theta, minus, when I multiply here, I get minus cosine 2 theta. So 2 of them minus 1 of them is 1 of them. So I have it factored. Well, now what do? We set each of those factors equal to 0, don't we? So we take the first factor, here it is, set it equal to 0. Take the second factor, here it is, set it equal to 0. And then we solve for the trig function. So what I did here on the left side, added 1 and then divided by 2. Over here on the right side, I just subtracted 1 on both sides. So I need to know what 2 theta has to be if the cosine of 2 theta is 1/2. Whoops. Well, I kind of bombed that here. Sorry about that. I clicked the wrong thing. So here's what I'm looking at. I draw myself a little unit circle. Here's where the first coordinate is 1/2, and so we've seen this idea. Then we could have an angle of pi over 3 or 5 pi over 3 or any angle that stops at this location. And so 2 theta, what we're taking the cosine of, could be pi over 3 plus any integer multiple of 2 pi. So that's what the plus 2k pi is for here. Likewise, what we're taking the cosine of, 2 theta, could be 5 pi over 3 plus any integer multiple of 2 pi. That's the plus 2k pi. And so all I've done here is I've gone through and multiplied by 1/2, so I get theta only. 1/2 times 2 theta is theta. When I multiply over here by 1/2, I get pi over 6 plus k pi. When I multiply over here by 1/2, I get 5 pi over 6 plus k pi. Now, we need only the thetas that are between 0 and 2 pi. And so I come back down here, and I say, okay, if k is 0, then this theta ends up being just pi over 6. If k is 1, then what I will get here will be pi over 6 plus 1 pi, what I've written. And when we add those together, we get 7 pi over 6. Now, I don't need to go any higher than 1, because if I made k equal 2, I'd get pi over 6 plus 2 pi. And that's automatically more than 2 pi, isn't it? So I just needed k equal 0 and k equal 1. Now, similarly over here, when k is equal to 0, I just have theta's 5 pi over 6. And when k is equal to 1, I have theta's 5 pi over 6 pi. And when I add those together, I get 11 pi over 6. So I actually have 4 angles that satisfy this part of the equation that comes from this factor. It's really easy to lose track. We haven't even dealt with this side yet, have we? That is the cosine 2 theta plus 1 factor. And here that turns into cosine 2 theta is equal to negative 1. So I'm thinking about, well, where is the cosine negative 1? It's over here at the position of pi, isn't it? And so what I know is that 2 theta would be, what I'm taking the cosine of, could be pi, or any time I'm left at this position, so pi plus an integer multiple of 2 pi. That's the plus 2k pi. And now I multiply through by 1/2 to get theta is equal to pi over 2 plus k pi. And now I need to decide, I need to find the values of theta that lie between 0 and 2 pi. So I try k equals 0. When k is 0, I just end up with theta is pi over 2. When k is 1, I end up with theta is pi over 2 plus 1 pi. And that ends up being 3 pi over 2. If I let k be 2, then I'd have pi over 2 plus 2 pi, which is already bigger than 2 pi, isn't it? So I just need k equals 0 and k equal 1 to find my theta values. And so now all I'm doing is going to next write the list in some kind of, some kind of order here. And so I started from the smallest, which was pi over 6, and then I found the next largest, and that's pi over 2, and then the next largest was 5 pi over 6, and then it was 7 pi over 6, and then 3 pi over 2, and finally the largest of the angles is 11 pi over 6, but all those are between 0 and 2 pi. So we have solved the equation. Okay, now we have a combination of double angle formula and inverse trig functions. And so we're asked to find the exact value of the sine of 2 times inverse cosine of negative square root of 3 over 2. Whoops. Well, I've clicked in the wrong place, didn't I? Well, here's the issue. We've got to remember that inverse cosine is really an angle. And so I've chosen to call the angle inverse cosine of negative square root of 3 over 2 by the name theta. Okay, so I'm just calling theta, or cosine, inverse cosine negative square root of 3 over 2 theta. Now, having done that, I know that means if the inverse cosine is equal to theta, then cosine of theta is equal to this argument, negative square root of 3 over 2. And furthermore, I know that theta has to be between 0 and pi, because the inverse cosine always gives a result between 0 and pi. Now, because the cosine of, you notice over here I've got in red, because the cosine of theta is negative square root of 3 over 2, if theta was between 0 and 2 pi, the cosine would be positive. But since the cosine is negative, that tells it has to be between negative pi over 2 and pi. So we actually know a little bit more about where this function actually lies. Okay, this angle theta. We don't know what it is, but we know where it lies. Okay, so since I've called inverse cosine theta, then this ends up being, our original problem ends up being the sine of 2 times theta. And that looks neater, at least it's easier for us to deal with. Now, the significance there is we recognize, and you're going to have to bear with me a little bit here. Well, I've overdone it here. Well, sorry, I clicked too much at one time. Let's pay attention to this side. Sine of 2 theta, based on the double angle formula for sine, is 2 sine theta cosine theta. Now, we already know from our labeling above that the cosine of theta is negative square root of 3 over 2. So we can make a replacement here. The question right now, though, is we don't know what sine of theta is. And so that's what I've got going over here on the left side. And if you look over here on the left side, then let's just pay attention. We go back to this identity. Sine squared theta plus cosine squared theta is equal to 1, and we know cosine of theta is negative square root of 3 over 2. So when I do the squaring here, I get positive 3/4, so I have sine squared theta plus 3/4 is equal to 1. Subtract 3/4 on both sides, and I end up with sine squared theta is equal to 1/4. Okay, so that means the sine of theta is either plus or minus the square root of 1/4. And we got to decide which it is. But remember what we just said above here. We said that we know, as far as that goes, we know theta is between 0 and pi. It's between negative pi over 2 and pi, but it doesn't really matter there. The sign in the first or second quadrant is positive. And so we know that we don't have a negative value, we have a positive value. And the square root of 1/4, of course, is 1/2. So now what I've done is I've put that 1/2 value in the place of sine theta right here. And then it's just a matter of multiplying. Of course, 2 times 1/2 is 1 times negative square root of 3 over 2. And so our final result in this case is negative square root of 3 over 2. Let me remind you that you can pause, you can rewind, and you can work ahead. So make sure that you use these videos in a way that's useful to you. Not only do you see what I'm doing, but make sure you spend enough time at them that you understand why I'm doing it. Well, we're at the end of this playing musical chairs here, it looks like, with my document. So we're at the end of this discussion on double angle formulas. Next, we're going to talk about, in the next discussion, a different video, we're going to talk about half angle formulas, and they're certainly related. So I look forward to you viewing that video.